Hey everyone, and welcome back to another High Yield Explainer. Today, we are tackling a massive, absolutely crucial topic for both your board exams and the wards: antibiotic resistance. Look, I know the sheer number of bugs, drugs, and resistance genes can feel super overwhelming. It's kind of like an impossible alphabet soup, right? But don't worry, today we are setting a really fast-paced, highly structured board prep tone. I promise you, by the end of this explainer, you're going to have a rock-solid framework that will literally stick in your mind for exam day and beyond. We are building a mental filing cabinet today, so you never have to rely on blind rote memorization ever again. Let's get into it.
Okay, let's dive right into our roadmap for today. First, the 3 resistance categories. Second, a deep dive into beta-lactamases. Third, target alteration, looking at MRSA and VRE. Fourth, high-yield drug resistance. And finally, number 5, urgent resistance threats. All right, section 1, the 3 resistance categories. So before we get into specific organisms or complex antibiotic classes, we have to understand the basic survival strategies bacteria use. Like I said, rote memorization without this mental filing cabinet, yeah, that completely fails under exam pressure. So here are the 3 core pillars of bacterial resistance. I really want you to mentally anchor every single bug we talk about today to one of these steps. Step 1 is target alteration or bypass. The bacteria just mutate the specific structure the antibiotic binds to, which instantly lowers the drug's binding affinity. Or they just create an alternative bypass enzyme. Step 2 is altered drug access. I mean, if the drug can't reach the target, it can't kill the bug. Bacteria pull this off by either decreasing uptake, like literally shutting down porn channels in their outer membrane, or by ramping up efflux pumps to actively spit the drug right back out. And step 3 is drug modification or inactivation. This is straight up biochemical warfare. The bacteria deploy enzymes that chemically modify or just completely destroy the antibiotic molecule.
Moving right along to section 2, deep dive into beta-lactamases.
Now that we've got our 3 pillars down, let's pivot and look at arguably the single most important resistance mechanism for gram-negative bacteria. This falls perfectly into that 3rd pillar of drug modification. We're talking about the Ambler molecular classification of beta-lactamases. This system basically categorizes beta-lactamases by their physical structure. Notice the really clear division here. Classes A, C, and D are all serine beta-lactamases. They use a serine amino acid right at their active site to attack the beta-lactam ring of the antibiotic. This includes your incredibly common ESBLs and KPC in Class A, AMP-C in Class C, and OXA48 in Class D. But check out Class B. Class B is the total metallic outlier. These are metallo-beta-lactamases, and instead of serine, they absolutely require zinc to function. The classic example you gotta know here is NDM. Keep that metallic outlier in your head because it changes everything about how we treat them. Let's rapid-fire the high-yield facts for the worst offenders. First up, ESBLs, or extended-spectrum beta-lactamases. They are infamous for chewing up 3rd-generation cephalosporins, like ceftriaxone and aztreonam, but they do not degrade carbapenems. Next is AMP-C. This one is chromosomally encoded in your escape organisms, like Enterobacter. When mutated, these bugs constitutively overexpress AMP-C, knocking out most penicillins and cephalosporins, but crucially, it's relatively stable to cephalosocotin and cefepime. Finally, KPC, Klebsiella pneumonia carbapenemase. This is a Class A serine enzyme, and it's the most common carbapenemase in the US. It basically eats all beta-lactams, carbapenems included. However, because it's serine-based, it is successfully inhibited by newer inhibitors like avibactam, varbactam, and drolibabactam.
All right, let's pause for a quick active recall check to test your immediate retention. Wake up your brains. Which carbapenemase requires zinc and is not inhibited by those massive new inhibitors like avibactam, vaborbactam, or rolibactam? Think back to that metallic outlier.
So, the crucial point is that the answer is NDM, the New Delhi metallo-beta-lactamase. Because NDM is a Class B metalloenzyme relying on zinc rather than serine, standard serine inhibitors like avibactam do absolutely nothing to it. NDM will just destroy carbapenems effortlessly. But here's the brilliant super high-yield workaround for your boards and the wards. NDM cannot hydrolyze aztreonam. Now there's a catch. Clinical NDM strains usually carry an ESBL alongside it that will destroy aztreonam. So the ultimate workaround is using a combination of aztreonam to bypass the NDM plus avibactam to inhibit the coexisting ESBL. It's literally a fascinating double-team strategy.
Section 3, target alteration, MRSI, and VRE. Now, while gram-negatives absolutely love deploying enzymes, remember that gram-positive bugs primarily rely on the first pillar we discussed, target alteration.
Let's look at a classic board comparison. First, MRSA. MRSA acquires the MECA gene, which encodes for PBP2A. This is an alternative penicillin-binding protein, essentially a bypass transpeptidase. It has an extremely low affinity for almost all beta-lactams, making them totally useless. The major exception you absolutely must know is ceftaroline. It is the only beta-lactam active against MRSA's PBP2A. Now, compare that to VRE, vancomycin-resistant enterococcus. VRE uses VAN genes to fundamentally alter the end of its peptidoglycan stem peptide. It changes it from D-ALA to D-ALA-D-lactate. That single structural change drops vancomycin's binding affinity by 1,000 times. And this brilliantly illustrates a completely different, almost physical defense mechanism when we look at VISA, vancomycin intermediate staph aureus. VISA doesn't change its target to lactate like VRE does. Instead, through multiple chromosomal mutations, VISA creates a massively thickened, poorly cross-linked cell wall packed with extra D-ALA residues. These extra targets act as decoys. They literally trap the vancomycin molecules in the outer layers of the cell wall. It acts like a giant molecular sponge, so the antibiotic can never even reach the active synthesis site where it actually does its damage. Pretty wild, right?
All right, Section 4, high-yield drug resistance. We're going to do a rapid-fire review of other major drug classes. Keep your energy high here because these are absolute classic board associations that test your fundamental understanding of our 3 core pillars. First up, aminoglycosides. The most common resistance here is plasmid-encoded transferase enzymes. These are acetyltransferases or phosphotransferases that literally add groups to the drug molecule, preventing it from binding to the ribosome. This perfectly illustrates the drug modification pillar. And remember, amikacin is less affected by these enzymes. Next, macrolides and linkosamides. Here we see ERM methylases. These enzymes actually modify the bacterial 23S RNA binding site. So while it's an enzyme at work, the ultimate result is actually target alteration. This causes cross-resistance to macrolides and clindamycin. Third, fluoroquinolones. This is pure target alteration, chromosomal mutations directly in the target enzymes, DNA gyrase and topoisomerase 4. And finally, tetracyclines. This is classic altered drug access. The bacteria use plasmid-encoded, highly specific efflux pumps to just bail the tetracyclines straight out of the cell.
Listen up, here is an essential exam tip and a critical clinical rule. Always use rifampin in combination. Why? Well, the mechanism of resistance to rifampin requires only a single mutation in the beta subunit of the bacterial RNA polymerase. Because it only takes 1 point mutation, high-level resistance emerges incredibly rapidly if you use rifampin as a monotherapy. Never, ever mix this up on exam day or when you're writing orders in the clinic. Finally, Section 5, urgent resistance threats. Look, it's really easy to get lost in the academic biochemistry of these mutations, but we have to recognize the modern, severe clinical realities of antimicrobial resistance. These aren't just textbook concepts anymore. They are daily crises in our ICUs. The CDC officially categorizes the most severe resistance patterns as urgent threats. These include carbapenem-resistant enterobacteriales, or CRE, which often utilize those exact KPC or NDM enzymes we discussed earlier. Also on the list is carbapenem-resistant Acinetobacter baumannii, known as CRA, and the increasingly difficult-to-treat drug-resistant Neisseria gonorrhea. Gonorrhea has sequentially mutated past almost every single class of antibiotic we've thrown at it, including widespread fluoroquinolone resistance. But honestly, perhaps one of the most terrifying modern realities is the emergence of the MCR1 gene. Polymyxins, like colistin, have historically been our toxic drugs of absolute last resort for highly resistant gram-negatives. They work by binding to the negatively charged cell surface, while the MCR1 gene encodes an enzyme that reduces that negative charge, basically blocking colistin from binding. But what makes MCR1 a massive public health nightmare is that it's plasmid-mediated. It's not locked in a chromosome. It is highly transferable between bacteria worldwide, threatening to take away our final line of defense. It literally spreads like wildfire. We categorize this resistance severity into 3 clinical tiers. MDR is multi-drug resistant, meaning the bug is resistant to 3 or more antibiotic classes, but several options still remain. XDR is extensively drug resistant. Here, the bug remains susceptible to only 2 or fewer classes, leaving us with very limited, often highly toxic options. And finally, PDR. This stands for pan-drug resistant. This is the catastrophic scenario where the isolate is resistant to absolutely all available antibiotic classes, leaving us with essentially 0 targeted treatment options.
So what does this all mean? With plasmids treating terrifying genes like MCR1 worldwide, Are we rapidly approaching an era of widespread pan-drug resistance? And more importantly for you, the next generation of physicians, how will our understanding of these core mechanisms, target alteration, altered access, and drug modification, evolve to help us stop it? I really hope this framework helps you dominate your exams and, eventually, helps you save your patients. Keep studying hard, use these mental anchors, and I'll catch you in the next explainer.